All right, welcome back, class. And so last video lecture, I went over activating groups. So it stands to reason that if there are things that are called activating groups, there are also things called deactivating groups, and that is true. And so let's look at an example of a deactivating group. So remember, when you have aromatic rings, monosubstituted aromatic rings, one of the things that comes up is that you can affect the rate of the reaction and the regioselectivity. So when I have a nitro group on there, this nitro group, remember, so when I draw the nitro group, there's a positive charge on that nitrogen, making that atom much more electronegative. So that's going to be pulling the electrons toward it from an inductive standpoint. Also, I can actually draw resonance structures in this case where the electrons are moving out of the aromatic ring, and that's going to deactivate the aromatic ring toward nucleophilic attack. And remember, in electrophilic aromatic substitutions, the first step is the rate determining step, the nucleophilic attack step. So if I do, so when I have a group that removes the electrons from the ring, we call that a deactivating group. And what we find is with this deactivating group that the regional selectivity is changed quite a lot. So the nitration of nitrobenzene is 100,000 times slower than benzene. So it's slower. And also in terms of the nitration, you get most of the meta product versus the ortho and the para product. So we say that this nitro group is a meta director. So we say that the nitro group is a deactivator. So it's a deactivator in terms of its rate. And it is a meta director in terms of its regioselectivity. And so why is that the case? Well, if we look at the attack again, what we have to do is we have to compare the stabilities of the three intermediates that form for the in each of the types of addition. So for example, if the double bond attacks and I put the nitro group in the ortho position, this is the intermediate that's formed. If the double bond attacks here and I put the nitro group in the meta position, that's the intermediate that's formed, the sigma complex. And then if I put the nitro group para, this is the initial sigma complex that's formed. And then you can draw the different resonance structures. So it would be good for you to maybe practice drawing these resonance structures. So if I draw these different resonance structures, what happens here is that this moves up, this moves over, and you end up with three resonance structures in each of the cases. Now, the reason why this intermediate is more stable is because if you look at these two resonance structures, the carbocation ends up next to the electron withdrawing group. See? So here, see how that carbocation ends up next to the electron withdrawing group? See how this positive charge ends up really close to the electron withdrawing group? You don't have that in the meta intermediate. So this meta intermediate is more stable because the positive charge stays the furthest away in every resonance structure. So this is then depicted visually in the reaction coordinate diagram. The meta intermediate is more stable than the para and the ortho, making the route to get to it faster. Now, one of the other things that we want to talk about in terms of activation and deactivation is the halogens. So we're going to go over what makes something an activator and a deactivator. We're going to go over a whole list of activators and deactivators in a minute. But before we do that, I want to go over the halogens. It turns out the halogens are kind of the exceptions to the rule. So it says all electron withdrawing groups are electron donating groups or ortho pair directors. All electron withdrawing groups are meta directors except the halogens. So it turns out the halogens are deactivating, so they withdraw via induction, but they also are ortho-para directing. So when you look at the intermediates, those ortho-para intermediates become more stable due to the electron donation. So the halogens are deactivating from an induction because inductively they remove electrons from the aromatic ring, making that nucleophilic attack harder to do. If these electrons are being pulled this way, the nucleophilic attack, that first step, becomes harder to do. And then you can also then, once you make the intermediate, once you make the sigma complex, so making the sigma complex here is harder in any case. Once you make the sigma complex, what you find is that the halogen then starts to act as an electron donating group. And so again, you end up with a fourth resonance structure for both the ortho and the para intermediates here. Okay, you end up with because you end up with these four resonance structures. The ortho and the para intermediates are more stable. Okay, so let me know if you have any questions about deactivators. So far we've gone over activators and deactivators. Try to absorb all of that in. Try to think about, try to understand like what makes something an activator versus a deactivator. What makes some things ortho-para-directors and what makes some things meta-directors. And then we're going to basically, you can kind of see what's going to happen next. We're going to go over a more extensive list of activators and deactivators. Thanks, and I hope that made sense, and let me know if you have any questions.